Hi, it's me, Tim Dodd, the Everyday Astronaut. Welcome to Starbase, Texas. Today we're going inside Starbase with the ultimate tour guide, Elon Musk. He's gonna take us through the high bay to see where starships are assembled. We'll also see the new mega bay under construction and talk about SpaceX's plans to get this rocket flying. Now I must warn you, some of the things we talk about are pretty technical, but I've got a handful of videos to help you understand what we're talking about. There's links in the description to those videos. And stick around because in the next videos, we're going to go up the launch tower, then we'll see the new Raptor 2s up close and personal, and talk about the Falcon 9's Merlin engine in great detail. And if you happen to find this video valuable, consider dropping a super thanks as a tip, or become a channel member or a Patreon supporter for early access and to help show your support. All right, let's get started.
So we're making good progress with the mega bay over there. So that should be done in a month or so.
That's tricky to scale from, because perspective wise right here it almost looks the same, you know, just from our perspective, but it's
about 30-40 feet taller.
Okay.
So it's more about you know, in this case girth is more important than length because we need to be able to construct more ships and boosters.
Yeah.
And you can see like the high bay there it's okay if you've got like maybe 2 or 3 works in progress, but or you like maybe have 2 or 3 workstations in this in the high bay. In the mega bay, we can have like really almost a dozen, maybe at least 10 workstations.
Holy cow.
So that's why the sort of width and length are more important there. Especially as we try to really get the production line going, we need more workstations.
Yeah.
The high bay here is okay for a low production rate, but as you go to a higher production rate, you just need more workstations.
Yeah. Yeah. And so that's a booster, right?
Yeah.
Or half a booster, half a ship, it looks like.
Yeah, exactly.
It looks like you do have those your vents there, the cold gas or the ullage gas vents.
Yes. Well, we're using the ullage gas for attitude control. So instead of having separate attitude control thrusters, we're using the ullage gas itself for attitude or reaction control. So basically for attitude control in once you're in orbit, or basically when you're in a vacuum, you don't need, the impulse needed is very low.
Yeah.
So in earlier design iterations, we had a separate cold gas attitude control system with nitrogen bottles, but that actually doesn't make a lot of sense since we've got a bunch of ullage that we're going to vent anyway. So we might as well use the ullage gas for basically attitude control and small delta V changes on orbit.
Yeah. I had to admit, you taught us to question your constraints. So
yeah.
That makes sense to me for the booster, you know, because the booster doesn't need to do it. Basically, the second you turn the engines off, it's going to want to vent a lot of its stuff anyway, and that's also corresponds with its first flip. But for a starship, like with docking maneuvers and stuff, to me, in my head, the Venn diagram of needing to depress a tank and the Venn diagram of needing to do an orbital maneuver don't always, you know, have a huge amount of overlap. So or is it not a concern? Is it always going to be on tap?
When the ship gets to orbit, you're going to have still a pretty high pressure in the oxygen and fuel tanks, which are autogenously pressurized. So you've got hot gaseous oxygen and sort of hot methane, but you have a lot more ullage pressure than you don't need. You actually don't need any more ullage pressure. So, like you've got more pressure than you need.
Okay.
So,
okay.
And the deorbit and the landing burns are done with the header tanks. So you actually want to vent the main tanks down to just above atmospheric pressure. Well, really, you want to have enough pressure in the main tanks for structural stability. So it's like this. So it's pressure stabilized, but not any more pressure than is needed for pressure stabilization for atmospheric entry.
Right.
And it's gonna, but when it gets to orbit, it's gonna have really a lot more pressure than is needed for atmospheric entry.
Okay.
So we would in any case end up venting the main tanks down to the pressure needed for reentry.
Okay.
So we'd be tossing that gas away.
Okay.
So
if it's free, you might as well use it.
yeah, we're going to dump the gas anyway. So then why have separate tanks and everything? You might as well use that gas for attitude control and small maneuvers, and then even then we'll still end up dumping the remaining gas that's not needed for entry.
Okay, so because of that last statement, you'll be dumping it anyway. Definitely kind of.
Yeah, actually, when you look at the old design, it's just like obviously it was pretty dumb to have a separate a cold gas reaction control system because we have excess ullage gas, and if we simply have main tank vents that vent in the direction that you'd want, then there's no need to have separate ullage thrusters. You can literally just use the vents.
So at some point, those will probably have like almost like an Apollo style, like four-way set of nozzles or something, right? Or because right now they're just facing prograde basically.
Yeah,
so,
that's those. So that would be for settling thrusters, basically, those ones up there.
Okay.
And there's side thrusters that you don't see on right now that'll be added. So side vents. Yeah.
So it just still surprises me that they're not doing, like capturing and doing some kind of high pressure or higher pressure, hot gas thruster anymore when you have.
No. The hot gas thruster was definitely over-engineered and unnecessary. So just using ullage gas for small thrust is the obvious move in this case. So in retrospect, the obvious move. It's much more efficient than having separate cold gas thrusters.
Well, I guess now that I think about it, there's never really been a rocket where the upper stage or the actual spacecraft is 99% a giant empty tank or a
yes.
drained tank. Every other vehicle, space shuttle, very small amounts of, just the ohms pods basically and
right.
that stuff. But there's never really been a vehicle that's on orbit where it just went through a, 4 or 5 minute burn. And now it needs to, that actually is really, really interesting. That's so crazy.
So it's a significant optimization, mass and cost savings to use the ullage gas for attitude and reaction control than to have separate cold gas thrusters.
I love it.
I'd say that's like one of the biggest improvements that we've made.
I gotta admit, that was when you were talking about that last time, and I kept thinking about
literally,
it.
It was literally occurred to me in real time. It occurred to me while I was explaining it to you. I was like, wait, what are we doing?
It was one of those things that kept just being like, that can't be right, but it is. It seems to be.
Yeah. But we kind of went through this exercise for the ship, and then it's like, wait a second, we should do that for the booster as well. And that just occurred to me literally while I was doing the interview with you. Like, okay. Do you mind saying a few things, or
sure. What do you think we should discuss?
Yeah, I want to see Elon's interviewing skills.
Well, I mean, so this is Joe Petrozalka. He's head of booster engineering, and I don't know if anything you want to say. could point at things and describe.
What's new on like 7 and stuff? What are some of the new things you guys are working on?
On Booster 7, which is down at the pad right now, it's been quite an improvement over the first boosters that we built, 4 and 5. We simplified a lot of things. Like there was a lot of, you just learn when you put things together the first time. We were able to get rid of a lot of it and combine a lot of it. It's got some new aero features, so it's got upgraded grid fins, and it has chines or strakes on the side of it, and those are going to make the re-entry performance much better, so we'll be able to actually come in at a lower velocity and get higher precision when we're coming in for the tower catch. So we're really excited to try that out on there.
Okay, then I got one for both of you guys. Why are the strakes or whatever
Chines?
Why aren't they 180?
Sounds like wind chimes.
Yeah, or like
just
chimes
with an N.
Chines.
Why aren't they 180 degrees to each other? It looks like they're about 140 or something offset.
Yeah, they're about 120 actually. And what they do, it's not about just increasing the like wingspan, if you will. It's about getting the area of the cylinder of the rocket to pressurize. So those features help the rest of the rocket pressurize, so it's more than just the area of those chines. You actually get more net drag on that section of the vehicle.
At an angle, right?
Not angle.
Yeah. Okay. So you're basically using that to increase like the overall surface area when it's coming at some kind of angle of attack.
Yeah, and so the booster is it's very bottom heavy with all of the engines down there, and so you're trying to actually add drag area down there as well.
Yep.
And when you do that, that can let the booster pitch up higher.
Yes.
Otherwise, if you don't have the chines, it wants to just come in
feet first. Yeah.
It's still going to come in pretty butt end first. It's a little slightly less.
Well, you can pitch it up to 10 or 20 degrees. And get much more control authority.
And further,
and
cross range.
As Joe was saying, it's a little bit more than just increasing the cross section of the vehicle.
Because you're not
trying to increase
in.
the integrated pressure profile on the base.
Okay.
So you've got the sort of the experienced wind is hitting the cylinder of the vehicle, and then it's rolling around the cylinder, and it's kind of like losing pressure as it rolls around.
Yep.
By having the chines be not at 180 degrees, but a little lower down, we're catching more of that air that's escaping.
Okay.
And so technically you actually have slightly less cross-sectional area, but you have more integrated pressure at the base.
Gotcha. Here, let's keep moving quick while this machinery's firing up. So,
but these are very primitive chines.
Yeah.
We can do way
This is
better.
our first attempt, and I expect to change them quite a lot over time.
Well, one of the things that I love about it is that you're covering up the COPVs, so it's both a COPV aero cover,
double use
out of it, which I love.
I do fear that it makes us less rigorous about getting rid of COPVs. But
more complacent that they're have a home.
As many as we wanted under them, so they were still a force.
Okay, good. But like if you say like what are optimized chines, you'd actually want them to get bigger as you get
wider at the bottom.
Yeah, wider at the bottom.
They begin to start looking like chip flaps.
Yeah.
Let the simulation run away.
Especially as you're coming in, like you said, with such a big amount of mass and basically a dry can above it, you'd really want the center of pressure to be as low as possible.
Right.
Yeah.
So that brings me to another question. Then I'm curious why you guys are still sticking with grid fins instead of like a more traditional, stabilator or some kind of canard or something,
Well,
this is a frequent topic of conversation.
Exactly. We discussed this a lot. I mean, essentially, like our optimization right now is getting to orbit.
Yeah.
So there's, So we know how to use grid fins from Falcon 9. Grid fins are much more consistent than flaps as you go from hypersonic to supersonic to transonic to subsonic. So you're going through these different Mach regimes.
Yeah.
And grid fins are much more consistent than a wing or a wingy thing.
A wingy, yeah.
So, especially as you go subsonic, the center of pressure on any kind of flat surface shifts significantly when you go from supersonic to subsonic. So, but could you be lighter than a grid fin? I think there's a good chance you could be. There's also another factor, which is the actuator power needed to turn a grid fin is much less than is needed to turn a wing, a sort of a wing-like thing.
Of similar.
Yeah, especially as that center of pressure changes.
It increases the torque on the motor, right?
Well,
you're
necessarily going to be
wrong.
wrong.
Is so short that even if the center of pressure changes, it's not far from the rotation point. And so the total torque required does not change dramatically throughout your Mach regime transitions.
Yeah.
But we are constantly talking about, do we have the right number of grid
Like
fins? Are they designed correctly?
Yes, so like we're not saying we're right, to be clear. Like we're definitely not optimal, but we it'll work. It's probability of it working is good, and it's one less problem to solve. It's also we obviously don't need 4. I think we could probably get away with 2. Definitely not more than 3.
Well, your old the 2016 original OG ITS had 3, and I remember that being a pretty unique design consideration, and
yeah, the sheer number of iterations that this vehicle has gone through is insane.
Before it even hit the pavement, it had already iterated so many times. Well, I started questioning, why. For me, I always thought the grid fin was a lot of it was being able to retract them on ascent, get them out of the wind stream. But now that you're not retracting them, I was like, well, that, and then also, the actual mass savings. 50% of the mass of a grid fin is perpendicular to your control motion. Your control authority. So I always wondered if how the trade would be on just compared to a normal wingy thing.
If you know your position well and you know your winds well. You can, in theory, have a ballistic arc when you do your boost back burn that is very accurate with nothing, except and we tried this in the early days of Falcon 9. But the problem is any small asymmetries on the vehicle will cause it to go crazy. Basically, it'll spin up and start flapping around, and it'll just start oscillating and rotating, and
dynamic stability becomes a concern.
Yeah. Exactly. So technically, you don't actually need massive surfaces. You just need to be able to take out the asymmetries of protuberances on the vehicle. And any error that you have with respect to position or your boost back impulse.
Yeah, and even wind conditions and things like that. I'm sure micro.
Yeah. So you really don't. The control surfaces you need are actually not very big, and we've shrunk the grid fins significantly from where we started out. They're much lighter. But even with grid fins, we really should be moving to aspirationally 2 grid fins, but certainly not more than 3. And the third one can be small.
Little vestigial guy in the. I like just imagining a tiny little guy on one sector. Yeah.
That's high bay. We have actually. This is the liquid oxygen tank section for booster 8. Is coming along very quickly right behind booster 7, and then the ship 24 nose cone. So this is the ship that we hope to pair with booster 7 for our first orbital launch.
It's looking so much more refined already than even S20. Oh, can we see the door? On the back side of it?
Corner.
Yeah, I mean, it's not gonna blow your mind.
You'd be surprised, man. The internet sure loves that door.
Yeah, you're gonna see the door anyway, so I guess why not? But
because you're at this point planning to launch 24 with Starlink version 2 already, right?
Yeah. We'll see. But I mean, it's just like I said. It's not going to blow your mind here. It's basically, it's like we call it the Pez dispenser, and it's kind of like that. It's the Starlink satellites are, in this rack, which looks like a friggin' Pez thing, because they're like, kind of like rectangular, just like a Pez, and they're stacked inside the nose cone, inside the fairing. And since they're low profile, we only need really a small door. With a small door, we can use pressure stabilization, like we can retain pressure in the fairing, so we can at least partially pressure stabilize the nose cone or fairing.
Gotcha.
And then we don't have a humongous hinge door yeah.
Like you might later on with,
with
larger pieces of cargo and things like that.
Yeah, we can make a giant door in the future, but this allows a small door weighs a lot less than a giant door.
Yeah.
It's the simplest answer we could come up with for deploying Starlink.
I feel like it's just begging
This
to
could
have
go wrong, to be clear.
Yeah.
Like if the mechanisms inside jam up, that'll be pretty embarrassing.
Right. But it looks like it's just begging to have like two big googly eyes with a funny looking grin there, or something.
Yeah. So we are incurring some complexity for the sort of the racking system inside, because you've got to have a racking system. So it's more complicated than a Pez dispenser, but it's the general principle is
Is it
similar.
like spring loaded then, or hydraulically loaded or something, or?
It's a bunch of electric. It's electric, and with a bunch of mechanisms.
And they just like roll themselves out and just zip out the door and. Sorry.
It's inspired by pallet stacking technology.
Yes.
Like go watch YouTube videos of a pallet stacker.
Yeah,
Gotcha.
exactly. Industrial pallet stackers is the same basic principle. They don't look super simple, but they do work.
Right.
And so it's the same basic mechanism. I mean, there's some risk of you're loading it in at 1G, and then you're unloading it at 0G. So, you could have some situation where you're unloading a mechanism, and because you unload the mechanism, it now binds.
Right.
So that's a risk that's hard to test for.
Yes. Yep. So you're planning to actually do your first set of Starlink version 2s on this vehicle, or wait, is this 25 or 24?
24.
This is 24, which is currently scheduled-ish to be the first orbital attempt, right? So has the plan changed to go from kind of a suborbital to an orbital launch if you're going to be trying to pop out a couple Starlinks?
No, we're always going to get, our next launch is always going to be orbital.
Is it full orbital, not?
Yes.
Okay, so that would...
Well, yes. I mean, yes, full orbital.
Because for a little while there was talk about like B4 and stuff and S20 back in the day doing like a just shy of orbit, on the re-entry by Hawaii and stuff like that, never quite reaching.
It's basically orbit.
Okay, yeah.
There's no real difference.
Mouse fart between the...
I mean, you could just, it's the difference between, you're going like 3/4 of the way around the Earth.
It's literally like 30 meters per second difference or something.
It's tiny.
It's hilariously small.
Yeah. It's extremely, it's essentially orbital velocity.
Yeah.
So there's just no point in doing, like, why do an extra loop around the Earth, and have the orbit burn. So,
but if you're
really, I wouldn't say that there's like high confidence that the first flight will work. I think there's a good chance that it does not reach orbit, that there's an issue with the booster or stage separation, or with the ship doesn't start, and then even if it does get to orbit, there's the probability that the ship makes it down intact is also not super high.
right.
This is why it's entering over the Pacific, an unpopulated area. So if there is an issue, it's not a danger to people.
Yep. So one of the things that a lot of people were asking about after, or once we started seeing the heat shield tiles, is why they aren't scaled like a Dragon or like a roof shingle where they're slightly overlapping and tapering in thickness. Why are they just have the gaps and everything?
There's multiple ways to approach this. So it's not that like a shingled approach couldn't work. You could have a shingled approach. the thing that will happen, or should in theory happen here, is that when the tiles get hot, they will expand and tighten the gap. So the gaps that you see here should be smaller when the tiles heat up.
Okay.
And you're really not going to see a lot of heat going down through those gaps, is our expectation. So shingling does not seem to be important. We could be wrong about that.
So it's going kind of around the vehicle as opposed to trying to burrow into it.
Right, right. Yeah, the flow is not coming straight in at those gaps. It's like...
yeah. I mean, we'll be coming in at an angle similar to the shuttle, like, I don't know, 60, 70 degrees. So it's sort of like if the ground is the surface of the Earth, we're sort of coming in like that.
Yeah.
And it's a balance between generating lift. Like for a reusable heat shield, we want to minimize the peak heat load.
Yep.
So the peak heat load is going to determine if we melt the tiles or not.
Yeah.
And if you melt the tiles, they're not very good for reuse. Right. So we're kind of balancing between generating lift and so there's atmospheric density, velocity, and you don't want to have like be going fast in high density air. That's going to be...
You want to kind of stay up in the upper atmosphere for a little bit longer than you would with...
You want to slow down as much as possible in the thin upper atmosphere, so you minimize peak heating. That's the goal. Minimize peak heating.
Which is pretty much what designed the whole shuttle's airframe. Almost was that peak heating and the controlling that peak Q.
Yes. So we're going to learn a lot from this first entry. And like I said, if there's any issues, the ship will not. If there's unexpected heating in some places, then the ship will fail on entry, and that'll be that. Yeah.
Is there any talks, speaking of failing and re-entry and all those things, have you guys, there were rumblings for a little bit that someone was talking about flying ship 20 still, or S-20, just on a suborbital.
Yeah, we've moved on.
Oh, just for my sake, man, those suborbital flights were so fun to watch because it was so slow. You got to feel it, that much longer when it's just sitting there, ascending for several minutes. Like, I've never seen anything like that.
Those flights are cool. But like this, we think we've learned, what we needed to learn really with the suborbital flights.
Yeah.
And there wasn't really much to learn, so best focus on getting to orbit.
Okay. I mean, yay, but also,
I'm quite excited about the
yeah, it's true. Those 33 Raptors, I think we'll put on that'll make up for the slow, gentle climb. Will be 33, shaking everything.
I think what'll seem kind of pretty odd or like strange is that the Starship orbital stack is going to come off the pad very fast.
Yeah.
So it's got a high thrust to weight.
What's its approximate thrust to weight?
I mean, it should be like 1.4-ish, maybe 1.5.
Around 1.5.
Yeah.
That's like Ariane 5 speeds with those SRBs. Once those light, that thing just shoots off the pad, and
yeah,
that'll be like that.
I mean,
That'll be disorienting to see something that big just accelerating that quickly. It'll.
For a reusable vehicle, you actually want to have a higher thrust to weight than an expendable vehicle, because thrust to weight below 1 is not doing anything.
Yep.
So your propellant is not being useful below thrust to weight of 1. So you actually want to have a higher thrust to weight for a reusable vehicle than for an expendable.
Yep.
For an expendable vehicle, the cost overwhelmingly is in the vehicle itself that you are losing.
Yes.
But for a reusable vehicle, if it's rapidly reusable and completely reusable, the cost of propellant is the single biggest cost of the flight. And so you want to have a high thrust to weight so that more of the thrust is useful.
Yeah.
So
high thrust to weight ratio literally is financially beneficial purely on the you need less fuel to do the same amount of work.
Like this may sound sort of mercantile, but it's actually the thing to optimize for is cost per ton to orbit. Like you can't cheat if you get cost per ton to orbit. It's not about what the mass ratio is or the ISP or anything. So although we're aiming for to have a great mass ratio, great ISP, everything, but it's really what is your fully considered cost per ton to orbit.
At the end of the day,
Yes,
that's
fully
all
considered cost per ton to orbit is the optimization.
Yeah.
And any given technology is only relevant to the degree that it reduces cost per ton to orbit.
So thrust to weight ratio might matter more than ISP as long as it makes for a lower cost per ton to orbit.
Yes.
So the trade-offs always end up with, does it decrease the cost per ton to orbit? And that's what matters more.
Aspirationally, like we don't always get it right, but the thing that really matters is minimize cost per ton to orbit, and then for Mars or the Moon, minimize cost per ton to the surface of the Moon or to the surface of Mars.
Yeah.
And just to give you a sense of just how much we need to improve it, it's really insane. Like right now, the cost per useful landed ton to the surface of Mars is in excess of $1 billion. So you can't count the heat shield or the parachute or the useful stuff.
Yeah.
So the landing system's mass does not count.
Yep.
Only like in the case of the rovers, it's really just the rover that is the useful thing.
Yep.
So if the rover weighs a ton, then and it costs $1 billion to get there, it's $1 billion per ton to Mars.
Yeah.
And that's roughly, what it currently costs. Now, in order to make life multiplanetary and have a self-sustaining city on Mars, that number will have to improve to, I think, probably under $100,000 a ton. That would be a 10,000 times better than the current state of the art. To put things into perspective, how much of an improvement is needed? Not 10,000%, 10,000-fold. That's what Starship is intended to do. Be 10,000 times better than the current state of the art. So
Orders and orders and orders of magnitude.
it's a lot of orders of magnitude. But it is, we're not breaking any laws of physics. It is possible to do that.
Should we, can we see up at the top, or is there anything to see up there right now?
Not really anything to see. I mean, I think we probably shouldn't take pictures of the inside. Not that it's super interesting, but but I think we got to be cautious about like pictures of the inside and stuff.
Where's the lifting points on this one now?
You can see the lugs up there. I mean, I'm not super, we need to move those lifting points. Those are not in a good position. So you don't have lifting points where the heat shield tiles are. We need to move the lift points to where the heat shield tiles are not.
Are you still hoping to catch the ship too with the arms, or what's the? I mean, you are, right?
Yeah.
How are you gonna catch it? I guess like, are you gonna do the same thing with the tiny little nubs, like the booster?
Yeah. I mean, it'll be very similar to the booster with. Now, in the case of the ship, because we need to have heat shield tiles that go more than 180 degrees, a little more than 180 degrees, we'll have to have the catch points kind of like flip out.
Oh, cool.
But it'll otherwise
So
be.
it stays in the leeward
It's got to be the
side
lee
then.
of the wind. Like you either have to. I mean, you either have to have a pot with heat shield tiles pop out, or have something that's in the leeward side that swings out.
Yeah.
One of the two.
And you can't just have you can't catch them by the nose fins.
You sort of could. Like what you're seeing there that doesn't have heat shield tiles will need to have heat shield tiles.
Yeah. Yep.
So everything's going to have heat shield tiles. That just you see like a steel part at the base of the, but that'll have to have tiles on it.
What if it's attached? If the mounting point would be attached to somewhere on the leeward side of the flap, and the flap could rotate more than 180 degrees, it could get in line with this. It could be the same mechanism that does the quickie thing. Could be just the flap itself.
I'm not sure I understand what you're saying, but
if the catch ball thing is on the leeward side of the flap, and the flap can go beyond 180 degrees.
Oh, that's man. That's not the problem you want us to try to solve. Like a huge challenge we have is the hot gas seal.
Right. You'd move that.
Yeah,
even
you
more
don't want to over center that.
Yes.
Frankly, the thing we need to do, I think, is move the forward flaps more towards the leeward side. This is a major internal debate, but
get them more out of
there's a massive amount of optimization possible with the forward flaps. They're in the wrong position. They're the wrong size, wrong position, wrong location. But they will work.
Yeah, they're a start.
Yeah, they'll work, but they're far from optimal.
What are the under those one heat shields? You see those like yellow puck things. What are those? And are those special or something?
Just temperature sensors.
Oh, cool.
I think so. Either temperature or radio. I'm not sure.
Okay.
So either the antennas or temperature sensors.
Well, what else is new since last time we were out here?
Well, we're building the mega bay.
What got your gears turning now?
No, just there's there's a lot of improvements to make with the ship and booster design. But anyway, right now the important thing is just to get to orbit with some reasonable payload, and then we have a whole series of improvements that we plan to improve the performance of the payload to orbit. But I really am not a fan of our forward flaps. Like every time I look at them, it drives me crazy because they're so suboptimal.
Well, at your rate of innovation and your rate of iteration, those will be different sooner rather than later, I'm sure.
Yeah, there's a potential scenario where we can delete the forward flaps entirely. And the shuttle doesn't have forward flaps.
Right.
So.
And that's because you're using dihedral control to control mostly pitch, and you can still do a little bit of yaw and roll with just a pair. So, because it's mostly about your center of pressure, right? So you
center of mass and center of pressure. It's a seesaw. So you can just think of these things like you've got a seesaw, and your center of, it's like your center of pressure, like the winds, the air is hitting the vehicle, and you have a center of pressure. It's like where's that air going to push the vehicle? Like if you add up all the wind pressure,
yeah.
If you're like pushing it with your finger, what's the center of that force going to be?
Yep.
And then you've got your center of mass, which is a similar thing but for mass. So you've got these sort of two seesaw things: center of pressure, center of mass. if you have big forward flaps and big rear flaps, you can have a much more variation in where your center of mass is going to be, and also what your angle of attack can be, and how you can control the vehicle in different macro regimes, and in the face of like a lot of wind shear, wind buffet.
So because there was that again Soviet I don't remember what it's called, the mole or something that just had a dihedral wing on the back. It was supposed to be like a mini shuttle for them, like a 2-passenger shuttle.
Baran, you mean?
What was that?
The Baran?
No, not Baran. No, it had it had foldable wings, and they basically, the only thing is those are fixed. They weren't dynamic, so it's not like they controlled its pitch, but it basically had was supposed to have a really high angle of attack during initial ascent, and then the back flaps just folded down. But that was to extend, basically have actual lift and do a horizontal landing. It wasn't necessarily like a dynamic link, but the idea was that you could control your overall, pitch, almost like, Virgin Galactic's Spaceship Two that folds in half, how it can change its whole center pressure and everything, just, in a single thing. But it's not, again, that's not dynamic. It goes from one mode to mode 1 to mode 2, and same with that Soviet one. But yeah, there's, that probably becomes a lot trickier when you are trying to be dynamic and when you are trying to actually pinpoint control your landing. I'm sure that with just having
the thing that's like really counterintuitive about the Starship is that it's not an aircraft, it's falling.
Yeah.
So we're just constantly trying to brake, as opposed to an aircraft is trying to generate lift and fly horizontally. We are trying to generate drag and be as draggy as possible when we fall.
Yeah.
So it's a very different optimization than an aircraft.
Yeah. Yeah.
So yeah. It's about 4 times the usable area of the high bay. So it's only a little bit taller, but it's a lot wider and deeper. And so we have a lot more positions for manufacturing the booster or the ship.
Yeah.
So if you have a production line, you need a lot of stations, essentially, for high production. So this is intended to have a lot of stations.
Is some of this getting replaced by another building that's like over top of some stuff? Or is it?
We are building a permanent factory building, and replacing the tents.
Okay. But the high bays and the mid bay.
We're not building a building to encompass the high bay. That would be insane. But we are going to be building a permanent factory building and replacing the tents. And we start the factory building from that side and kind of build and gradually replace the tents with a large permanent building.
Okay. And that's actually currently in the works, I guess. So you're still, there's a lot of speculation, obviously, with how quickly Florida's ramping up, that this might be slowing down, but that doesn't seem to be slowing down too much if you're building a building out here. Yeah. Hey, by the way, I'm Tim.
Hi.
Hey,
Andy
nice to
Krebs.
meet you. Awesome. Yeah, sorry, what was your name?
Andy Krebs.
Okay, cool.
I do engineering for the non-flight hardware. So I do the high bays in the factory. I'm responsible for those, as well as the launch pad.
Cool.
Stage 0. A lot of the Stage 0 stuff.
Yeah.
The ground systems especially inclusive of the tower, are at least as complicated as the Stage 1 or Stage 2.
Yeah.
So.
Should we go check out Stage 0?
Sure.
Thank you, Elon, for all your generous time, and thank you, Ryan Chilinsky, for helping shoot and capture this incredible conversation. Thanks, everybody. That's going to do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.